So we've talked about functions holomorphic at infinity. What about holomorphicity to infinity? So infinite outputs. So in this situation, so we ask the following question. So can we view functions with poles these are maybe meromorphic functions with poles as maps to P1? Well, the answer to this question, as we expect, is yes. Right? And we give a definition. Okay, so let's let U be open, be a region. So region's a connected open set. So let F be a holomorphic function except for at some point. Okay? And then we say that F defines a holomorphic map to P1 or an analytic map to P1 if and only if the function g of z is equal to 1 over f of z is holomorphic near z is equal to z naught. So again, by holomorphic here, so holomorphic map to infinity, so holomorphic map to P1 if and only if this thing holds. So again, this means we're using analytic and holomorphic are the same thing, and that this has a power series, a convergent power series in some neighborhood of z is equal to z naught. That's what we mean by this. So let me just make a quick remark here. So note. So holomorphic at infinity. So what we do is we check f of 1 over z at 1 over zeta, let's say, at zeta is equal to 0. Okay, is checked. Okay, and then we have the other condition is that holomorphic to infinity, or to P1, here, this means that 1 over f of z at z is equal to z naught is checked. Okay, so this thing here is the infinite input. And here is when we have an infinite output. Okay, so the lemma that I want to show is the following. So let f be a holomorphic function on this connected set minus a point. Okay, and f defines a holomorphic map. A holomorphic map to infinity. This condition here is the same thing as f is meromorphic. At this thing. So this is the two things that I want to say is that, okay, so we have defining a holomorphic map is the same thing as being meromorphic. Okay, so proof, let's do the proof. Okay, so suppose f is a meromorphic function on U. Okay, so okay, so let's recall what this means. That f here, we're saying that it's holomorphic at these points, the points away from z0, is meromorphic at z0 if and only if the Laurent series, which we showed existed, expansion at z0 has an infinite tail, or has a finite tail. Finite principal part. Okay, so what does this mean? So therefore, so we may write. So we're supposing that it's meromorphic. So we may write that f of z looks like p of 1 over z minus z0 plus h of z, where here, so where this guy here, h, is holomorphic near z is equal to z0. So I'm using holomorphic and analytic are the same thing, so that there's a paraseries, and p of z, this guy here is, this is a polynomial with vanishing constant term. And this holds in an annulus, so like a punctured disc, since we're, Okay, so then to check holomorphicity at infinity, we use the definition. So to infinity, we define, we use the definition. Okay, so let me write down the definition. So we take g of z, and we define it to be the reciprocal here. And this is 1 over h of z. And check that, so we define this, so we define g of z, and check analyticity at z is equal to z0. Alright, so what does this mean? So, well, okay, so let's do this, okay? So we'll let d be the degree of the polynomial, d be the degree of p, okay? And what we're going to do is we're going to modify this guy, so g of z, so this is equal to z, let me just get rid of this a little bit, z minus z naught. So I'm just going to multiply the numerator and the denominator here by this polynomial. And what we've done is we made this thing so this thing is no longer having poles. D. Okay, so the denominator, okay, so this guy here is non-zero at z is equal to z naught. So that'll show that this thing here is non-zero. So this thing vanishes. Okay, so this tells us that G of z is holomorphic, or locally analytic, since the denominator is denominator is a non-vanishing, is holomorphic and non-vanishing at z naught. Okay, so what do? We used the definition here of what it means to be meromorphic, so that there's a finite principal part. So this is where you don't let essential singularities happen. Then we use that definition to show that meromorphic implies that it's holomorphic at infinity, using the definition of holomorphic at infinity. Holomorphic to infinity, not at infinity, to infinity. Okay. So conversely, let's suppose that suppose f is holomorphic to infinity at z is equal to z naught. Okay, so we may write well, g of z has to have a particular form using the definition. So that's the definition of g of z. But this looks like some guy here. Right? And so this thing here just looks like z minus z naught to the m, h of z, where, so we're using the fact that it's holomorphic there, where h of z is analytic, z naught and h of z naught is not equal to 0. Okay, so this implies that f of z, so just flipping everything again, looks like 1 over z minus z naught to some power, h of z. And this thing can be written as 1 over z minus z naught to the m plus this guy, some power series here. So now that this guy, this guy, inverse. Okay? Sorry, we have to flip this. So we just flip both of these guys. And this guy is not 0, so then it has a power series. Great. So, okay, so this shows that it's meromorphic, right? Okay, because it has a finite tail. Again, so what did we show? We showed that being holomorphic at infinity is the same thing as being meromorphic. Okay, using the definition of having this guy having a power series locally. Okay, as a corollary, this shows us that the meromorphic functions on C are really just the holomorphic functions. So this is meromorphic at every point. Are just the holomorphic maps functions which are holomorphic as maps to P1 to the complex projective line. Okay, so that's kind of interesting, is that now we can recast meromorphic functions. So we did it locally for there, but meromorphic functions are really just the holomorphic functions from the complex numbers to P1.